I recognize this is not the ideal situation to try to learn some complicated topics in calculus, but we're just going to have to, do the best we can and go from there. So I'm making this video to talk to you about a couple of things. We're going to talk about the first derivative test and how to use that to find local extrema. We're going to also talk about concavity and points of inflection. So talking about what it means to say a function is concave up or down, and then what it means to have an inflection point. And then finally, we'll talk about some of the similar kind of things, but using the second derivative test. Now, I just want to make another kind of pitch before I get into this about reading the actual text, right? This is the textbook digitally that's on Google Classroom, and also the Calculus for Dummies, on differentiation. I've talked about, reading this as well. I recognize that you guys have a lot of classes, a lot of things to do, but, if you look at some of this stuff, we already went through differentiation rules, so you can skip through all that. But, if you start in chapter 11 in Calculus for Dummies, differentiation, shape for curves, a lot of the stuff we're talking about is explained here in a much simpler way. So I would encourage you to check out chapter 11 in the Calculus for Dummies, which is on Google Classroom. Anyway, okay, let's get into it. So we're going to start with looking at the first derivative test, okay? And like I said, I want you guys to read either in the textbook, this section 4.5, the introduction will talk to you about this stuff, as well as if you want to look at the Calculus for Dummies, it'll help you walk you through all this stuff. I'm going to focus on using these tests to help solve these problems. So I'm going to use the problem solving strategy here to find all these extrema. We're going to do this example together in a second to find all the local extrema using the first derivative test. Okay, so first thing we're going to do is to find critical points, which we did in a previous lesson, so that should be okay. We're going to use those critical points to divide up the domain of our function into smaller intervals, and then we're going to use test points that are in those smaller intervals to analyze the signs of them. And based on those signs, we're going to determine if we're going to have any local extrema happening at our critical points. Okay? So let's start with the first one here. We have this cubic polynomial with 4 terms. And the first thing I'm going to do is I'm going to find the derivative. Okay, so f prime of x is equal to d dx of x cubed minus 3x squared minus 9x minus 1. Okay, now we've done this many times. This is a polynomial, so just take the derivative of each term. We have 3x squared minus 6x minus 9. So that is the derivative. Again, like we talked about in the previous lesson, critical points are whatever is going to make this derivative, right, this first derivative, undefined or equal to 0. This is a quadratic trinomial. We don't have any values for x that are going to make it undefined. So really, I just need to focus on whatever makes this equal to 0. So I'm going to factor out a 3. That leaves me with x squared minus 2x minus 3. Okay? So now I'm going to factor, and I'm going to get x minus 3 and x plus 1. Okay, so my 2 critical points for this function are positive 3 and negative 1. That's kind of the first step here to using this first derivative test. Okay, so at this point, after finding my critical points, the domain of my function is negative infinity to infinity. So when I look at breaking this up into smaller intervals, I'm going to use the intervals negative infinity to negative 1, negative 1 to 3, and 3 to infinity. So if I look at the signs of when I plug in some test points within these intervals in my first derivative, I can use that information to determine if I have any local extrema at these critical points. All right, so I'm going to go to the next slide here. All right, I'm going to make a table. All right, this table's got a lot going on, so make sure you're writing small. All right, so the first thing I'm going to do is I'm going to have my interval. All right, so my interval is going to go first. So I'm going to have negative infinity to negative 1. Then my next one is -1 to +3. And then finally 3 to infinity. So I got kind of 3 different intervals that I need to test out. Okay, so my test point, right? My test point just needs to be some value that's within these intervals. All right, so I'm going to use -2. I'm going to use +2. And then I'm going to use 4. Excuse me. Now you can use, there are more options here, right? I chose -2 for the first one. You could use -3, -4, -5, whatever you want, guys. It's your choice. The next one, I'm going to probably actually need to use some space out here. So this will be my conclusion. And in here is where I'm going to do my sine when I plug it into the first derivative. So sine when you plug it into the first derivative, so f of your test point. Okay, now let me write the first derivative again so you know what I'm plugging it into. Plugging it into 3 times x minus 3 and x plus 1. So this, I'll highlight it. This always helps my brain. So I'm using this to find essentially my most important column. Okay, so if you want, right, I mean, you guys have Desmos at your fingertips, so feel free to just plug in these values, my test points, into this, and you can find the sign of whatever it spits out. But I want to go by what, essentially what you should be doing to do the calculus, and I don't care about the actual value, I just care about the sign. So my 3 is a positive, all right? -2 minus 3 is a negative, and -2 plus 1 is a negative. So a positive times a negative will be a positive. Okay, so same thing for +2. The 3 is a positive, 2 minus 3 is a negative, oops, and then 2 plus 1 is a positive. So a positive times a positive is a negative. If you're like having trouble with this, I think the easiest way is just to count the number of negatives. If you see an even number of negatives, you know it's a positive. If you see an odd number of negatives, you know it's a negative. Finally, the last one I'm testing, that 3 in front is a positive, 4 minus 3 is a positive, and 4 plus 1 is a positive. So everything's positive there. Okay, so now what you're noticing that's happening here is that the function, right, when I plug these in, you notice my signs are changing as I go through my test points. So that means that when I look at this, the f of x function, right, my conclusion, if it's positive there, if the first derivative test is showing me the derivative is positive, then the original function f of x is increasing. Same thing if it shows me in the first derivative test that my in my interval the derivative is negative, then my function is decreasing. And finally, same thing as the first test point, this says my original function is increasing. Now, this is going all the way back to your work in pre-calculus, but if your function is going from increasing to decreasing, that's going to cause a local maximum. And then if your function is decreasing to increasing, that's going to be where we have a local minimum. So what this means in terms of our extrema is that at these critical points, right, remember our critical points were -1 and 3, we have something happening at each of these. So at -1, if we're going from increasing to decreasing, we have a local maximum at x equals -1, and we have a local minimum, since we're going from decreasing to increasing, a local minimum at x equals +3. So, I feel like this lesson is really just a solid continuation of the previous lesson. Okay, now let me show you, on our graphing calculator with Desmos, kind of summarize, hopefully, in your brain what all just happened. All right, so I'm going to type in the original function, x cubed minus 3x squared minus 9x minus 1. So we have x cubed minus 3x squared minus 9x minus 1. and we looked at critical points were, here we go. Critical point was -1 and +3. And you can see this confirms that we have a local maximum at -1 and a local minimum at +3. So that, in essence, is how you use the first derivative test to find your local extrema. Okay? So we're going to do the same thing, right? Exactly the same thing with one more example. Okay. So I'm going to first find the derivative. So f prime of x is d dx of 5x to the 1/3 power minus x to the 5/3 power. All right, so there's a lot going on here. I'm going to use the power rule. So 1/3 times 5 is 5/3. And then that's going to be x to the, got to subtract 1 from 1/3. So that's going to be to the -2/3 power minus 5/3 times x, and then 5/3 minus 1. So 5/3 minus 3/3 will be 2/3. Okay, I'm going to take the time to clean this algebra up. So I'm going to write this as 5 over 3 times x to the 2/3 power minus 5 over 3 times x to the 2/3 power. I need to get a common denominator, so I'm going to multiply the fraction on the right-hand side, which needs x to the 2/3. So I'll show my work here. So multiply the top and bottom times x to the 2/3 power. Make sure you know that that's in the exponent. There we go. So now that's going to give me 5 minus, now watch what I do here. All right, x to the 2/3 times x to the 2/3, you're going to, since you're multiplying with the same base, you're going to add the exponent. So 2/3 plus 2/3 is going to be 4/3 all over 3 times x to the 2/3 power. All right, so this is it. You could keep going if you wanted to. I know the book factors out the 5 in the numerator. It's your choice, right? We can do that when we solve. But ultimately now I need to figure out what makes this derivative equal to 0 or undefined, because that's going to be where my critical values are. I'm going to start with the undefined because that's rarely something that we have to worry about. But you'll notice in this denominator we have the variable x, and it's raised to the 2/3 power. So if you wanted to think of this as 3 times the cube root of x squared set equal to 0, all right, essentially you're going to see that 0 squared, the cube root of 0 is 0, 0 times 3 is 0, that x equals 0 is going to be one of my critical values, or my critical points, I should say, because it makes the derivative of this f of x function undefined. So that's one of my critical points. Another critical point, or two of them actually, are going to come from the numerator. So if I set the numerator equal to 0, right? So set that equal to 0. Move the 5 over, or I guess you can just move the negative 5x to the 4/3 power. Divide by 5. You get this. We actually solved this in the previous lesson, this exact equation. What I did was I took the 4th root, which means I had to use plus or minus, and then the cube root of, or I should say cubing a negative and a positive gave me the same thing. So you should notice that my other critical points are plus or minus 1. So I have 3 critical points here. So I'm going to cut up, if you will, my domain of -infinity to infinity into these, using these 3 critical points. So I have -infinity to -1, -1 to 0, 0 to 1, and then 1 to infinity. So I'm going to have a lot more test points when I make my table. All right, so I'm going to make the same table that I just made. Obviously, it's not going to be exactly the same, but the same idea here. Okay, so we have the, oh, guess I shouldn't have done that. My bad. Okay, so we have our interval. Let me write those down. So -infinity to -1, -1 to 0, 0 to 1, and then 1 to infinity. So those are the 4 intervals that I'm going to be testing. Okay, next thing is our test points. All right, so my test point just needs to be some number that's in between here. So I'm just going to use -2 for this one. And then between -1 and 0, I'm going to use -0.5, +0.5, and then +2. Again, you can use any point you want. That's probably the most common ones you'll see in this problem. Then I'm going to evaluate, remember the signage when I plug this in. So the sign, when I evaluate this at the derivative of my function. And my last thing is my conclusion. Okay, let me write down the derivative again so you know what I'm plugging into. The derivative of this function is 5 minus 5 times x to the 4/3 power all over 3 times x to the 2/3 power. Okay. Now again, please feel free to use Desmos if you want, right, to plug in these numbers. You can get the actual value. I just care about the signage. So I'll go ahead and type this in just to show you it's okay to use Desmos to find the signs. I'm just going to make a table with this value here. So we have 5 minus 5x to the, was it 4/3? Let me just confirm. Oops, where is it? There it is. Yep. Okay, so that, I want those parentheses. There we go. All over 3x to the 2/3 power. Let me make sure that's right. Yes. Okay, I'm going to make a table. Don't worry about the sketch right now. So I have, what did I say I was using? -2. What I was using? Yes, and -0.5. And don't worry about 0, +0.5, and +2. We'll just delete this one. Okay. Those are the numbers that I was using. And if you look at the signs, it's a negative, positive, positive, and a negative. Negative, positive, positive, negative. Okay. So my signage is going to be negative, positive, positive, negative. So here we have f of x is decreasing because the sign of my derivative of f of x over this interval is negative. Here the function, actually the next two, the function is increasing. And then finally, the last one, the function is decreasing. So now when you finish this, right, when you finish this problem, you'll notice it wasn't all nice and cookie cutter like the last one. We're going from decreasing to increasing between my first two intervals. So at -1, there is going to be something happening. So we're decreasing and then increasing. So a local minimum. So local, not locat, local minimum at x equals -1. And then you'll notice at 0, we go from positive to positive, so it's still increasing. So you'll see what happens at when I go to 0 on the original function, but no extrema happening at 0. And then finally at +1, if we're increasing to then go to decreasing, that is a local maximum at x equals +1. Okay, now let's go to Desmos and type in the original so you can get a clear picture of everything that's happening. All right, so the original was 5x to the 1/3 power. So we have 5x to the 1/3 power minus, let's see, it's minus x to the 5/3 power. Okay, so I'll zoom in here. we had our extrema. We're at -1, 0, +1. And you'll notice we have our local minimum at -1, local maximum at +1, but we don't have any extrema at x equals 0. All right, so that's it so far on the first derivative test. That's how you kind of go about doing this. Hopefully not too bad, especially if you took the time to read in the textbook or in the Calculus for Dummies section, chapter 11. It should help your brain understand some of this stuff. Okay, let's move into concavity and points of inflection, testing for concavity, and then we'll move into something called the second derivative test. Again, I cannot stress enough here that this is just a quick breeze by some of these concepts that, guys, I know this is not the best way to learn calculus by watching a video from your teacher, so I really apologize. But please do everything you can. And if you're not reading the textbook or if you're not reading Calculus for Dummies, there are some things you can still do. So try to carve out time. I know you guys are super busy, but please do your best on that. Let me show you something I think will help with understanding what concavity means. So concave up or concave down. There's a lot of technical words going on here, right? The idea here is that if you are increasing, right, if your function is increasing and you look at the derivative of that function is also increasing, that we say that it's concave up, all right? And if you look at the function or the derivative and it's decreasing, we say it's concave down. So let me kind of show you something that, I didn't draw this. I just snipped this from something, but zoom in for you, I think. Maybe not. Oh, well, you can see it. Essentially, this is something that the Calculus for Dummies will help you to kind of remember, or I'm telling you right now, but the idea is that if a function is concave up, right, you will notice that it kind of looks like it might be a cup. So if you kind of focus on the parabola part of this cup, right, holding water, so this is concave up, and so this is also concave up. What's interesting, though, guys, is a lot of students have the trouble differentiating between, and that was not a use of differentiation like calculus, but just kind of deciding between things that are increasing can be concave up or concave down, and things that are decreasing could be concave up or concave down. So make sure you are, kind of understand the difference between those. So concave up, think like a cup, and then concave down, think like a frown. If you think of this frown, this parabola that's upside down, it can't hold any water, so these would be concave down, all right? And it's fun because it rhymes. Okay, let's talk a little bit. Oh, I should say one last thing. In calculus, we define something as an inflection point if your function changes concavity at that point. So like in this little diagram, this is right here, we are decreasing, okay, to increasing, but this whole time you're actually concave up, right? Think like a cup, even though we have a local extrema here. Then we have our inflection point. So now we have concavity going down, so concave down. Here's our inflection, or excuse me, here is our local maximum. So now we're moving to decreasing, but we're still concave down like a frown. So that's the kind of the confusing part, but this will help you. There's also a really good diagram in Calculus for Dummies in chapter 11. All right, let's do some of this work using this information about testing for concavity here, okay? Okay, so for testing for concavity here, first thing we're going to do is we're going to find the second derivative of this original function. So the function is x cubed minus 6x squared plus 9x plus 30. So let's find the first derivative. So d dx of x cubed minus 6x squared plus 9x plus 30. So that's going to be 3x squared minus 12x plus 9. Okay, now we're going to keep going, right? I want to find the second derivative of this function. So another derivative, d dx of 3x squared minus 12x plus 9. So that's going to be 6x minus 12. All right, so the way to test for your concavity here is to find, there's not really a technical definition of the points I'm going to find right now, but in Calculus for Dummies, what we talk about is we just say that these are essentially finding the critical points at your second derivative. So in the previous problems, we've been finding critical points of our function by looking at what makes our derivative equal to 0 or undefined. So if I look at what makes this second derivative equal to 0 or undefined. These are in, I'm putting air quotes here. I know you can't see it, but air quotes are the critical points of your first derivative. Okay, I know that's kind of confusing, but kind of work with me here. This is a linear function, so I'm not worried about anything being undefined. So I just need to figure out what makes it 0. All right, so solve this like you did when you guys were in Algebra 1. Who knew when you were in Algebra 1 that you would be help understanding how to find your concavity as well as your inflection point? So x equals 2. So taking these intervals, or this domain of negative infinity to infinity, I'm going to split that into negative infinity to positive 2 and 2 to positive infinity. All right, so I'm going to use this to make one of those tables like we did before. Okay. Now this is very similar to the table that we made before, right? Not going to be, doesn't need to be as large because we only have 2 intervals that we're testing. But essentially, all right, I'm going to be looking at my interval. Then I have my test points. Then I have my signage. But again, this is going to be sine of the second derivative now, so a little bit different. And then our conclusion. All right, so my intervals are negative infinity to positive 2 and 2 to infinity. All right, so test point could be 1 and 3. Again, you can use 0, negative numbers, whatever you want. All right, so let me write down my second derivative. I believe it was 6x minus 12. Confirm. Yes, 6x minus 12. This one should be hopefully a little easier. You can do this mentally. Plugging in 1, you get 6 minus 12, which is a negative. And then plugging in 3, you get 18 minus 12, which is a positive. So this conclusion is that your original function is concave down. All right, so think frown in the interval negative infinity to 2. And then f of x is concave up, or think like a cup holding water, in the interval 2 to infinity. So because we're changing concavity from negative, so down, to positive or up at x equals 2, so x equals 2 is an inflection point. All right, so our ordered pair for this inflection point is going to be 2 comma whatever it is when you plug in 2 to the original function, right? So if I go back to the original function, right, that's x cubed. Let me do it real quick. So f of 2 is going to be 2 cubed minus, I think it was 6x squared. Let me just confirm. 6x squared. Yes, plus 9x plus 30. So plus 9x plus 30. So that's going to be 8. 2 squared is 4. Minus 6 is 24. Plus 18 plus 30. So that's going to be negative 16 plus 18 is 2. 2 plus 30 is 32. Don't really need to know that. You're going to see it on the graph. But just want to show you that that's what is an inflection point. Okay? So let me type in the original function here so I can show you what everything is kind of happening for your brain in the graph. All right, so I'm going to type in x cubed minus 3x squared plus 9x and then plus 30. All right, where are we at here? Let me do a table so we can zoom in. Don't need to do a table, but I wanted to zoom in and get it. There we go. That's much better. Move this out of the way. Okay, so we have our, you'll notice that we are increasing the whole time, right? So we're increasing the whole time, but our concavity, right? If you think of like this is, your frown part. So we are concave down for this first part until x equals 2. So right here, what did I do wrong? That should be not 44. What did I do wrong? Hold on. Let me pause for a second. Okay, I figured it out. That's my bad. It's minus 6x squared. Excuse me. Let me get this table out of here. Okay, there we go. That's better. So you can see that we are concave up, or excuse me, concave down as we're increasing here because this is like part of a frown. And then at 2 comma 32 right there, all right, at 2 comma 32, we are actually, we're still increasing, right? Or I should say we have switched concavity here, that we've gone from our, we're still increasing, but we've switched from concave down like a frown to now to the right of this looks like part of a cup or holding water. So we've switched to concave up. So when you switch your concavity, that means you have an inflection point. So at 2,32, we have an inflection point. Okay, let's move to the last thing. The last thing is looking at something called the second derivative test. This is really just kind of what formalizes a lot of the stuff we've been working on. All right, so essentially, if you find that you have a value that makes the derivative equal to 0, so you have a critical point, if you look at the signage of your second derivative at that value, if it's less than 0, then it's going to be a local maximum. And if it's greater than 0, it'll be a local minimum. Now, if it's equal to 0 when you plug it into the second derivative, then the test is inconclusive and you have to do a little bit more kind of working to figure out what's going on there. Okay, so let's find the second derivative to look at the local extrema for this problem. Okay, so the first thing you want to do in order to use the second derivative test, first thing we need are the critical points of this function. So we're going to find the derivative of f of x, which is d dx of x to the fifth power minus 5x cubed. So that's going to be 5x to the fourth power minus 15x squared. And we're going to try to figure out values for x and make this undefined or equal to 0. This is a polynomial, so with no issues in terms of undefined values, but I can figure out what makes it equal to 0. So if I do some factoring, I'll factor out 5x squared, and I'm left with x squared minus 3. This one, hopefully you see, is pretty straightforward. 0 squared times 5 will be 0. This one, if you move the minus 3 over, you get positive 3, and if you take the square root of both sides, you get plus or minus the square root of 3. So essentially, the second derivative test says to take these critical points and evaluate them into the second derivative, and that signage, all right, those values, when you look at the signs, will tell you if you have any extrema at those critical points. So I'm going to find the second derivative now, which is d dx of 5x to the fourth power minus 15x squared, which is 20x cubed minus 30x to the first power. All right, so if I make a table here, so I can make a table on the next slide. If I make a table, all right, where I have my critical points of negative square root of 3, 0, and positive square root of 3, and I want to plug it into the second derivative, so here are my critical points, then I can make my conclusion based on the outcome. So I'm going to go to Desmos and make a table for this second derivative, and I can figure out what kind of extrema, if any, I have at these critical points. Again, I don't want you guys to be too worried about this. We're going to have lots of time to practice before we take the test in, about a month. Actually, I think it's exactly a month today, December 9th. But the key thing is that you'll get to see how this will look on the AP exam. Okay, so let's type into Desmos. Let's type in second derivative, which is 20x cubed minus 30x. 20x cubed minus 30x. I'm going to make a table. And my points are negative square root of 3 and the 0 and positive square root of 3. Okay, all these other ones I can just delete. I don't need them. All right, so if I look at the signage here, when I plug in the negative square root of 3, I get a negative value. And when I plug in the 0, I get 0. And then when I plug in the positive square root of 3, I get a positive. So this is a negative, this is 0, and this is a positive. Now I'll get back to the 0 in a moment. But if I use the second derivative test, right, I'll highlight this for you to help show you what I'm looking at. Right, I think this image is helpful. Right, but we know already these are critical points because they make the derivative of my f of x function equal to 0. And if you look at if your second derivative at that value is less than 0, then you have a local maximum. So that would be happening in my first one here, right? So this is my local maximum value. And then it says if you have, right, the second one here, if your value when you plug it into the second derivative is greater than 0 or positive, that is your local minimum. So this is my local minimum. Now let me talk to you real quick about what happens when you get 0, right? This is inconclusive. So you actually have to go kind of back a step and do the first derivative test, which we did at the very beginning of this lesson. And the way you do that is, if you remember, we would break down this domain into our subintervals, right? Instead of negative infinity to infinity, I'd have negative infinity to the negative square root of 3, negative square root of 3 to 0, 0 to the positive square root of 3, positive square root of 3 to infinity. Now, I'm not going to need to do all of it like I did before because I already found my extrema at negative square root of 3 and positive square root of 3. So, kind of what your takeaway from this lesson is going to be is a lot of different ways to find the same kind of stuff. But I want to focus on the ones that have 0. Okay, so what I'm going to do is I'm going to make a mini table, kind of like one that we made earlier, not in this problem, but in a previous problem. So you're going to notice it's going to have a lot more columns here. So we have our interval first, which is, let me make it a little bit wider, negative square root of 3 to 0, and then 0 to the positive square root of 3, so that's the interval. Then I'm going to use my test point, right? So test point, which I can use negative 1 is in between there, and positive 1. Then I want the sine, right? This is the first derivative test now. Sine of the first derivative, and then my conclusion. Okay, so let me write down the first derivative. That was 5x to the fourth power minus 15x squared. That's the first derivative. So if I plug in negative 1 here, right, negative 1 to the fourth power is going to be positive. Negative 1 squared is a positive, so 5 minus 15 is a negative. If I plug in 1, same thing, I get 5 minus 15, which is negative. So f of x for both of these, right, intervals is going to be decreasing. All right, so if you're not changing from decreasing to increasing or increasing to decreasing, you don't have any local extrema. So this, right, kind of arrow down here to say C, the first derivative test, right, kind of had to do another test for 0. At the critical point 0, we don't have any local extrema. Okay? All right, so let me graph this for you, and then we'll be done with all this information from this lesson. So let me graph the original function, x to the fifth power minus 5x cubed. So x to the fifth power minus 5x cubed. Okay, so again, we're honing in on 3 points here. Our negative square root of 3, positive square root of 3, and then we have 0. So you'll notice that we have a local maximum at negative square root of 3, a local minimum at positive square root of 3, and we don't have any extrema at x equals 0. So that's it, guys. I recognize this is a long video. I apologize in advance. You're probably going to take a couple of days to watch this. Take Thursday and Friday to help you watch this, and do your best to try practicing over the weekend. Stay positive. I'll be back as soon as I can, and good luck.